webcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Welcome to today's webinar hosted by the Oracle User Group and Oracle Partner Viscosity North America. My name is Monica Lee, and I am the Marketing Director for Viscosity. We are a full Oracle Stack consulting firm with core expertise in Oracle database, including RAC, Apex, zero downtime migrations, performance tuning, and high availability. During today's presentation, please feel free to submit questions to Maria, our presenter today, in the questions prompt seen on the GoToWebinar panel. And she'll address whatever she can following the presentation. So today we've got NYOUG President Coleman Leviter. He's going to introduce a little more about NYOUG, and then he's going to introduce Maria to you. Go ahead, Colgan.
Thank you, Monica, for the introduction. Again, welcome to our webinar series. We've had a lot of talented Oracle community speakers, and I just want to give you a brief overview of the New York Oracle Users Group. We were founded in 1984 for the exchange of ideas, assistance, and support of the Oracle products. Connect with us through Twitter, through Meetup, LinkedIn, Facebook, and of course our website, nyoug.org. Also outreach to our membership through the Oracle User Group community at Oracle's website at community.oracle.com/community/user-groups. And all these slides I'm showing you are available on our website as well. And I wish to thank Viscosity for hosting the series, and I wish to introduce our speaker today, Maria Colgan. Maria is a master product manager at Oracle Corporation, has been with the company since version 7.3 was released in 1996. Maria's core responsibility is to advocate for the Oracle database and best practices for incorporating it into your environments. She's also responsible for getting the feedback from our customers and partners incorporated into future releases of the product. Prior to this role, she was the product manager for Oracle Database In-Memory and the Oracle Database Query Optimizer. Maria, thank you again from the community for presenting this very important topic about the Explain Plan.
Thanks, Coleman. It's a real pleasure to be here with you guys this morning. And as Coleman said, the topic I'm talking about today is Explain the Explain Plan. Because it is such a big topic and there's so much to cover, we're actually going to do today's webinar in two parts. So part one will be for the next 45 minutes. And then next week on August 18th, we're going to do the second part of the presentation or the webinar. And all of the slides and the material that I'm going to cover will be made available to you. We're also recording both sessions, so if there's something you want to go back and listen to in the future, that will be made available to you as well. Okay, so now that we've got all of our housekeeping done, why don't we jump in and get started? And we're going to start at the very beginning just to make sure we're all on the same page with what is an execution plan. And really what an execution plan is that need to be executed in order to answer your particular query. So in the example you see on the slide there, I'm doing a two-table join between products and sales. And traditionally, when we ask to see the execution plan, we see it as a table and a set of steps or operations in that table. And those operations are either going to produce rows, consume rows, or they're going to do both, produce and consume rows. So let's look at what operations would fall into each category. So a full table scan is a great example of an operation that produces rows. A sort or a group by is a great example of an operation that simply consumes rows. And as something like a hash join or a nested loops is an operation that will both consume and produce rows, sending them on to the next step in the plan. Now, as I said, traditionally it shows up as a table, but actually inside in the code, it actually shows up as a plan tree. And by default, these are left deep trees. In other words, the first step in the execution plan is always shown in the lower left-hand side of the table. So in this example, the very first step we're going to do is that full table scan of products, and rows are going to flow out of that full table scan to the hash join. Now, in order to do the join, we need two inputs, and since we only have rows from the product table, we'll go down the other side of the tree, and the second operation in this case will actually be the table scan of sales. As soon as it begins to produce rows, it sends them to the hash join, and the hash join can then begin. And as I said, it both consumes rows and produces rows, because as it does the joined rows or the matched rows will pass on to the group by, which will be the final step in this plan. So although most of the tools that we use show it as a table, it is actually really this tree structure that actually gets built inside in the code. Along with the table with the list of operations, we also get a lot of other useful information underneath the execution plan. And the first part of this information is called the predicate information. In other words, the optimizer is sharing with you how it's using the where clause predicates that you supply in your query. And it uses those where clause predicates in two different ways. It either uses it to help find or retrieve the data, and we call those access predicates, or we use them as a filter after the data has been found. So in this example, let's focus just on access predicates initially. And with access predicates, what those where clause predicates will do is tell us where we should get the data from. So for example, it could be a start or a stop key for an index, or it could simply be a set of row IDs that are being supplied to a full table scan. Either way, they'll show up as an access predicate in the predicate information section underneath the plan, and each one of those predicates will have an ID number in front of them, and that ID number actually matches to the corresponding entry in the execution plan where that where clause predicate is being applied. So in my example here, very simple, this where clause predicate, prod ID equals 139, is being applied as part of the index range scan on the my prod index, or line 2 of that execution plan. Now, as I said, your where clause predicates fall into one of two categories, access or filter predicates. If your where clause predicate isn't going to be used to help us retrieve the data, then it's going to be used to help us filter out unnecessary data after the data has been retrieved. In other words, we'll read all of the data and then we'll filter out the bits we don't need. And so this tends to be non-equality where clause predicates are used typically as filters. In my example here, it's a like predicate that has been treated as a filter predicate. Underneath the predicate information, you then get a note section, and the optimizer developers have made a huge effort, especially in the more recent releases, to share a lot more information about what the optimizer is up to and how we came to this execution plan in that note section. So it'll tell you if you're accidentally using the rule-based optimizer, which of course is no longer supported. It was deprecated way back in Oracle 8i, but it is still there. Just if anybody is wondering, it is still there. It still can be used, but we will alert you to that in the notes section and suggest that you move to the cost-based optimizer. But it also tells you other information. For example, I've used dynamic sampling for this particular plan because one or more of the objects in the query didn't have statistics, or maybe because you asked us to, but we do alert you to the fact that dynamic sampling was used. We also alert you to the fact if there was some kind of plan mechanism used. So for example, was a stored outline used, a SQL baseline, or a profile? All of that information is in the notes section, as is information about adaptive plans that were new in 12C, and we'll talk a little bit more about those later on in the presentation. And also, of course, starting in 19C, one of my favorite new features is hint usage. So if I'm supplying hints to my optimizer SQL statement, there's now a whole new section that appears underneath the plan by default that tells you whether or not there was an error with your hint, whether it was unused for a particular reason, whatever it is, it gives you all of that hint usage information underneath the plan in 19C. Okay, great. So we now know what the plan is. How do I go about generating a plan? Well, there are a ton of tools available to you that show you the plan. Whether you want to use SQL Developer, you're using TK-Prof, you're using SQL Monitor reports or AutoTrace, whatever tool it is, underneath the covers, there's really only two ways to generate those plans. You can either use the explain plan command, or you can look in the $SQL plan, which was introduced in Oracle 9i, that shows you the actual plan that's in the shared pool or inside the cursor cache inside the shared pool for that SQL statement. Now, you want to be careful, although explain plan is super useful because you don't actually have to execute the SQL statement in order to see the plan. There are certain occasions, especially if you're using bind variables, where what you see with explain plan is not actually the plan that will be used when that SQL statement is executed. The reason for that is the explain plan command is not bind aware, so it doesn't peek at those bind values, which is why it doesn't potentially show you the plan that you'll get if you were to go and execute that. So typically, if I'm debugging a situation, especially if somebody's reported a performance problem, I'm going to use $SQL plan as the way to look at those. So let's take a look at both approaches though, because if I'm in a data warehouse where I'm not necessarily using as many bind variables, perhaps I'm using literal values because, as I said, it is a warehouse. These are queries that aren't run that frequently, then explain plan will be just fine. So here's a quick example of how I do it. I'd say explain plan for, give the SQL statement, and then once that says it's been explained, then I want to retrieve the plan, and I do that by taking advantage of a built-in package inside the Oracle database called DBMS XPlan. And there's a function in there called display, and it's going to take 3 arguments. The first argument is, the first argument is the plan table name. You should just let that default. It's plan table is the default name, but I don't even bother supplying it. If you leave it blank, it will find your user's default plan table. The statement ID, again, you can leave it blank. There's no need to pass that in. And the last parameter, the most powerful one, is the format. And I'll spend a lot more detail in just a moment explaining that format parameter, but just know that that's the third argument. If, on the other hand, I'm actually looking to see what was the actual execution plan for this SQL statement as it was executed, i.e. it's still in the shared pool and I want to see that plan, then I want to take advantage of the same package, DBMS XPlan, but this time I'm going to do display cursor. Now, if I leave the first 2 arguments null, as I have in this example, what that's going to do is it'll show me the execution plan for the SQL statement that was previously executed within this session. So oftentimes I'll execute the query, and then immediately after that, I'll run the command you see on the screen there, where I call DBMS XPlan display cursor. So you'll notice it's a different function. I leave the first 2 arguments blank, which means I want you to show me the plan for the previously executed SQL statement. But if you don't want to do that, if you don't want to execute the SQL statement because you know it's already been executed by somebody else, you're going to need 2 additional pieces of information to show the plan. You'll need the SQL ID, which we can grab from $SQL, and the child number. By default, it always shows you child 0 for that plan, so you are going to need to supply that child number. And again, the third parameter there is format. Now the format, as I said, is going to be incredibly useful. You'll see me do lots of different tricks with that parameter in order to show additional information as we go through the presentation. And I'm going to share that with you as we go, so you too can understand how powerful that format parameter is. We also have a very detailed blog about that format parameter on the Optimizer blog. Super easy to remember, blogs.oracle.com/optimizer. Once you go there, there is a huge raft of information about the Oracle Optimizer, including details about how to display that plan. Whew. Okay, so we've covered the 2 basics. What is a plan and how do I generate one? But now let's dive in and understand actually how we can read and what information is shared in an execution plan. And I've broken it up into 4 key areas. I'm going to cover the first 3 today, and then we'll cover the rest of them in next week's session, along with some advanced topics like partitioning and parallel execution. So let's start with the most important part of the execution plan, and that's the cardinality estimates. And what is that? Well, it's the estimated number of rows the optimizer believes this operation or this step in the plan is going to return. Now, it's based on, or how the optimizer comes up with this, is using your statistics in a whole number of formulas that it has. The more complicated your where clause predicate is, the more complicated these formulas are. And you certainly don't need to understand the formulas, but I wanted to show you a brief example here, just so you can see what stats are being used. So if you imagine I have a simple SQL statement, I'm accessing one table, that table has 100 rows, and I have a where clause predicate that says where column 1 is equal to a value. The way we would come up with the cardinality estimate in this case is we would take the total number of rows in that table, which is 100. We're going to divide it by the number of distinct values that are in column 1. In this case, that's 5 distinct values. And the result of that formula is the cardinality estimate. So 100 divided by 5 gives me 20 rows. So the optimizer is going to estimate 20 rows will be returned for my query. As I said, the more complicated the predicates, the more complicated the formula, but you get the idea. We're using the basic column and table level statistics to come up with these cardinality estimates. So why should you care? Why is it such a big deal? Why am I starting with this? Well, the cardinality estimate really influences the optimizer's decision for the next steps in the plan. So for example, if the cardinality estimate is rather large, and these rows are flowing into a join, maybe we'll pick something like a hash join or a sort merge join instead of a nested loops, which might have been a good choice if the number of rows flowing in was very, very small. So if the cardinality estimates are wrong, then it can really affect the other choices the optimizer makes in the plan. So it's really a good idea if I'm looking to diagnose a performance problem or look at things, I want to start by looking at the cardinality estimates. Now, you and I are going to see this same plan multiple times today, and we're going to use it as our example plan because it's going to have a lot of useful things for us to look at. But what we look at here can apply to any execution plan. So when I'm looking at this plan and I'm looking for the cardinality estimates, I'm going to look in the rows column. That's going to list the cardinality estimate the optimizers come up with for every operation in that plan. Now, how do I know if those cardinality estimates are good or not? Well, I could look at the individual where clause predicates that correspond to the different rows or entries in our execution plan. So for example, if I look at the filter predicate, department name equals sales, that's used on line 6 of our plan, which is a full table scan of the department, it says there's an estimated 1 row return from the departments table where the department name equals sales. And chances are we only have one department whose name equals sale. So that seems like an accurate cardinality estimate. I could also do a select count star from departments where department name equals sales to confirm that. And that would be an easy way to check the cardinality estimates. But when things are a little more complicated, it can be difficult to have to do a select count star for every where clause predicate or for predicate information I have under the plan. So a much simpler way to do it is to add the gather plan statistics hint to my SQL statement and change the format parameter so that when it displays the execution plan for me, then it will say I want to change the format to all stats last. In other words, give me all of the statistics you have for this SQL statement for the last execution. And when I do that, what you find is additional columns will start to appear in our plan table. So instead of having just rows as the column in the table, I now have E rows or as well as A rows. So E rows, estimated number of rows, A rows, actual rows being returned by each one of those steps in the plan. And these two columns appear next to each other in the table, making it nice and easy for you to be able to do that direct comparison between the estimated rows that the optimizer thought should come back and the actual rows we saw during execution. Now, there are a number of other additional columns that have appeared as well. So, for example, we have a new column appear in the table called starts, and that indicates the number of times that step or operation in the plan is going to be executed. Now, most of them appear to be executed just once in my example here, but you'll notice there that the table access on sales has actually been started 28 times. And the reason for that is the sales table is partitioned. There are 28 partitions in the sales table, and so we scan, because they are separate structures out on disk. Each partition is a separate object or a separate structure, and because of that, we will start that scan of the sales table 28 times, one for each partition. That's why you see the start column there saying 28 for the table, but you don't see that for products because it's not a partition table. It is just one object. Now, you'll see starts also a lot if you do nested loop joins, which tells you how many times we went through the inner table for based on the values coming from the outer table. And we'll talk more about that when we get to the join section. The other additional columns you get is you get buffer information. So how many buffers were needed to be read for each step in that plan. And you also get quite a bit of detail about memory, how much memory we believe may be needed to conduct this query, especially to conduct this query in a single pass, as well as how much total memory was used. Again, less important for transaction processing style queries, very important sometimes for large analytical queries where you're trying to size your PGA appropriately to ensure that the majority of the work, the joins and the group bys, all can take place in memory. Now, if we look at the example I'm showing you now, I've done all the tricks that I just told you. I've added the gather plan statistics hint to my query. I used the format all stats last to show me the A rows or the actual rows. But then when I look at the plan, I don't see the information I'm expecting. I see a whole bunch of zeros in the A rows, but 71 rows were returned to the end user. So I know there were rows produced. What happened? Why don't I see all of the information that I'm expecting? Well, the reason we have so many zeros is that this is actually a parallel plan. In other words, parallel server processes or parallel execution was used to execute this plan. And what I asked Oracle to do was show me the statistics or the execution statistics for the very last person to execute this cursor. Well, with parallel execution, the very last person to execute the cursor is actually the query coordinator, who normally doesn't do any of the work in the plan. In fact, the query coordinator writes his name or her name in the plan. You see it there, line 1 of our execution plan, PX coordinator. And the PX coordinator only does the work that happens above that step in the plan. Everything else that happens below that, so everything from step 2 all the way through 13, is actually done by the parallel server processes and not by the coordinator. That's why we have zeros in all of those steps in our plan. So how do I get to see that information? How do I see what the coordinator did and what the parallel server processes did? Well, I'm going to need to change my format parameter. Instead of being all stats last, I need to do all stats all. Show me all of the statistics you have for all of the people who've executed this cursor. Now, this trick works really well as long as that statement has only been run in parallel once, because it's, remember, aggregating all of the sessions values for the execution statistics. And if it's been executed multiple times, your A rows will actually show a much higher value than is actually true for a single execution, because it will aggregate all of the times that cursor has been executed to generate those stats. So what do I do if I need to diagnose a parallel statement that has been run more than once on a particular system? Well, unfortunately, the only way I know how to do that is to take advantage of something called SQL Monitor. Now, the reason I don't base this whole session on SQL Monitor, even though I think it's a fantastic tool, is because it is a paid option. You do need the diag and tuning pack in order to be able to use SQL Monitor on an Oracle database. So that's why I use the very basic tabular execution plans for this entire session, because that's completely free and available to everybody. SQL Monitor does need those additional licenses, but if you're doing a lot of diag and tuning for data warehouses or for systems that use a lot of parallel execution, it may be well worth the money to invest in the diagnostics and tuning packs, because then you'll have access to SQL Monitor. SQL Monitor always shows you actual rows as well as estimated rows, and it always gets the count for actual rows correct, even for parallel statements that have been executed multiple times, because it records information for just a single execution. So if I am doing that, then I would highly recommend you use SQL Monitor. Okay, so what happens when I look at my execution plan, I follow all of the steps you've given me, Maria, and I realize my cardinality estimate isn't accurate? What can I do? First thing I would look for is, do I have any stale or missing statistics? Remember, I said dynamic sampling may show up in the notes section underneath the plan if you've got missing stats. That'd be the first place I would look. Do any of my tables have missing or perhaps stale statistics? They haven't been gathered in a really long time. Is there a data skew in one of the columns in my tables? In other words, by default, the optimizer assumes we have an even distribution of rows to values in a column. So if we remember back at the beginning, I shared an example that said I was selecting from my table where the column 1 equaled a value. And the cardinality estimate is divided the total number of rows in the table by the number of distinct values in that column. And the reason the optimizer uses that formula by default is it assumes that you have a uniform distribution or an equal amount of each column value across the rows in that table. So again, I had 5, there were 100 rows in the table. The optimizer assumes that 20 rows of that table have value 1, 20 rows have value 2, 20 rows have value 3, and so on. In other words, there's an even distribution of those distinct values across the rows in the table. Now, there's lots of cases where that's true, or at least approximately true, but there are also just as many cases where it's not true. So for example, I may have a data skew. Some products may be more popular than others. Some zip codes for our customers will be more popular than others. And for those types of columns, it's very beneficial to have a histogram to be able to tell the optimizer about that data skew. So that may be a reason why you're not getting the cardinality estimate you're expecting. Another place that can mislead the optimizer when it comes to cardinality estimates is when we use multiple where clause predicates on a single table. Now, when you go to SQL School initially, one of the things you're told when you're writing queries is be as selective as you possibly can. Give the optimizer all of the information you have so that we can filter out any unnecessary rows and only return what we're really interested in. And that is true. And the optimizer is geared to assume that each additional where clause predicate that you supply will actually reduce the number of rows being returned by your query. So for example, if I say where column 1 equals 5 and column 2 equals 10, the optimizer assumes that additional where clause predicate will reduce the number of rows being returned. And typically that's true, unless those columns have a real world relationship or correlation between those columns. A good example for this would be something like state and zip code or state and country. So for example, if I have a query where the where clause predicate says New York and the country is equal to USA, the optimizer assumes the additional where clause predicate of USA will reduce the number of rows, when in fact it won't, because New York, the USA is the only country that has the state New York in it. So the additional where clause predicate is actually going to throw off the optimizer's cardinality estimate. And so we need to tell the optimizer about these real world relationships among the columns in our tables. So the way we're able to do that is we can create extended statistics and tell the optimizer, hey, when you see state and country used together, there is actually a real world relationship between those columns. And so you want to use the column group statistics, or statistics that I'm going to gather on these columns as a group, rather than the individual statistics. The same is true if we are going to use functions on our columns. So, or a function wrapped column is often how you hear this being described. So for example, upper last name equals something. As soon as we put that upper function on the last name column, we're basically blinding the optimizer. The optimizer has no idea what that upper function is going to do to the values inside in that last name column. And so it effectively guesses at what the cardinality estimate should be. Now, in older versions of the Oracle database, you would have been told the way to fix that problem, the way to give the optimizer the correct cardinality, would be to create a function-based index on upper last name so that the optimizer can use the index statistics to get a good cardinality estimate. And that is a very valid solution. But starting from 11G onwards, you can also create extended statistics. So you can create extended stats for that function wrapped column, and that way you don't actually have to make for being used as an access method. You can use extended stats instead. So one of the most common questions I've got is, I have a function-based index, should I drop it and use extended stats instead? And my answer to that is always the same. If the index is never used as an access method, it's only there to supply the optimizer with statistics, then go ahead and switch to extended stats and mark the index invisible, just to be sure no one's using it. As long as no one starts screaming that their plans have regressed, you can go ahead and drop that index. But if the index is being used as an access predicate, it's helping speed up your queries, why not just leave it and continue to use the index for the stats? So that gives you two ways to solve the same problem. Another case where using multiple columns can actually be put off the cardinality estimate is when we're doing joins. So I'm using multiple tables, or multiple columns, sorry, from two tables as my join condition. Just like with the where clause predicates, the optimizer assumes each additional join predicate that you're going to add to that query will reduce the number of rows being returned via that join. If that's not the case, then we will have a cardinality misestimate. So to fix that, you might want to create extended statistics on both sides of the join. So all the columns used in both tables would be, you'd create extended statistics on both tables for those join columns, so that when the optimizer is determining the cardinality estimate for that join, it will use the extended stats on both sides of the join to determine that correct cardinality for the join. But you need those extended stats on both sides in order for that to happen. The final tip I'll give you is whether or not you should in fact tell the optimizer to use dynamic sampling. I mentioned earlier that it's typically used by default when we've sales statistics, but there are some cases where you may actually encourage Oracle to use dynamic sampling, and that's if you've got very complicated formulas in your where clause predicate, especially if those formulas come from columns that are from different tables. So for example, if I was trying to work out the final cost of an item and I had the unit price plus the sales tax to get the final cost of the object or the item, then I may be getting the column values for the tax rate or the tax amount coming from a different table from the original unit price. Complicated formulas where I'm doing addition or multiplication or stuff like that in those formulas, dynamic sampling level 4 or above can be incredibly useful to help get the correct cardinality estimate, because again, the optimizer has no idea what the relationship is between these columns across tables. And so dynamic sampling can help us, even though it will extend the parse time while we go out and sample a small set of the blocks from these tables, work out actually how many rows do satisfy this where clause condition, and then extrapolate from that small sample to what the cardinality estimate would be for the whole table. It may be worth it. Again, more information on dynamic sampling is available on the optimizer blog. Okay, so now we've covered cardinality estimates. Let's look at access paths. Now, one of my favorite things to ask when we do this webinar in person is I'll often ask folks in the room, how many access paths do you believe the optimizer has at its disposal? And remember, access paths are the way we get data from the database. Now, most people, I normally get a couple of answers. The first answer I get is 2, index, full table scan. And to be honest, you can divide all of the access paths Oracle has into just those 2 categories. But when I say I want, then people start throwing out much larger numbers. Maybe there's 20, maybe there's 25, maybe there's 50. Turns out there's 9. Oracle only has 9 access paths available to it. So it's actually very easy for you to understand what these 9 access paths are and when the optimizer is going to apply them. So let's go through the 9 options it's got. First one, the one that we all know most about, full table scan. What does it mean? It means I'm going to read all of the rows in that table. I'll filter out any of the rows that don't meet the where clause predicates that have been supplied. And this approach is typically taken when there's no index or if a parallel degree has been specified on that table, making the full table scan a lot cheaper. And I'll talk all about that and the impact of parallel execution in next week's seminar. But just so we know, full table scan, going to read all the rows in the table, filter out what we don't need. Table access by row ID is also a very common one. And what it means is that the row ID is going to be supplied to that full table scan. So what is a row ID? A row ID is an address or an indicator that tells me in which data file and inside which data block in that data file I'm going to find a particular row. So along with the data file and the block number, I also get the offset or the location of that row inside the block. That's what the row ID is. It's basically a shortcut to a particular row in a table. And so when it's table access by row ID, those row IDs are either supplied via an index access or perhaps directly in the where clause predicate, but they're going to give me that shortcut to find the rows I need in the table. So let's move on to indexes now. An index unique scan is probably the most preferred execution plan. Why? Because only one row is guaranteed to be returned by that operation, the volume of data that we need to operate on. So an index unique scan is fantastic, but it's only going to be used if the table in question has a unique or a primary key index specified on it, and we have an equality predicate on that primary key or unique key. That will give me an index unique scan. Much more common is an index range scan. An index range scan accesses adjacent blocks with adjacent leaf blocks inside of my index. And what it does is it returns the row ID values for the entries in those blocks. Now, it's used if I have an equality predicate on a non-unique column or non-unique index, and it's also used if I've got a range predicate on a unique index. So if I have where the primary key is between 8 and 24, then instead of an index unique scan, I'll actually get an index range scan. An index skip scan is a lot less common, certainly in the older versions of the Oracle database. In more recent versions from 12c onwards, you actually may see an index skip scan more frequently. What it means is that the where clause predicates you have include where clause predicates on the other columns in the index, but not the leading column, not the leading edge of that index, whatever the first column is in that index. And so an index skip scan says we're going to skip over that first value in the index because the subsequent values you've got in that multi-column index do have where clause predicates on them, and they're actually very selective. In other words, there's a high number of distinct values in those subsequent columns, meaning that the index could still be very valuable to us because it will help reduce a large number of rows that we need to operate in. So as I said, typically done when the leading edge or the first column in that index doesn't have a high number of distinct values in that column, but the subsequent. A full index scan doesn't actually read all of the blocks in that index the way the name would imply. You do read all of the leaf blocks in the index, but you only read enough of the branch blocks in order to find that first leaf block. Now, it is typically used to do a full index scan if all of the columns we need for this query are present in the index, and the order by clause that you've got in your query also matches the order that we find these indexes in the index, or sorry, we find these columns in the index. The reason why that correlation between the order by and the index is if the columns in our index match that order by clause, then we've already got the data in a sorted format, and we don't need to do an additional sort operation to satisfy that order by. The fast full index scan, on the other hand, does read all of the blocks in the index, and it's effectively a replacement for a full table scan. So instead of reading all of the blocks in the table, I can read all of the blocks in the index because that index has all of the columns that I need to answer this particular query. And this is the only index access path that you can do in parallel. That's right, a fast full table scan does use multi-block read and can be done in parallel. Again, we'll look at this in more detail next week. Last two are probably less common than the ones we've looked at before, but still quite valuable. An index join happens when I've got a very, very wide table that has multiple indexes on it, and two or more of those indexes accommodate all of the columns that I'm looking for in this incredibly large table, and it's more efficient for me to scan two of these indexes and hash join them together to get the result set rather than scanning the entire table. As I said, it's less common to occur, but it does occur if I've got incredibly wide tables that are also rather large. You can get an index join as an access method. The final one is if you take advantage of bitmap indexes, and this is typically more common in a data warehouse, especially if you've got a star schema style schema inside that data warehouse. You'll create bitmap indexes. What bitmap indexes are is they contain a key value and a mapping function that's going to convert each bit in that key into a row ID. And the reason why we use them so frequently in data warehousing, especially for star schemas, is that bitmap indexes can be and or together based on your where clause predicates. And we can manipulate these keys, keeping the volume of data we're manipulating incredibly small, because as I said, they can be and or logicked together to come up with a final set of row IDs so that we only go to the table once and apply this combined bitmap to extract the row IDs that would perhaps satisfy multiple joins in that particular table or in that particular query. Okay, so where do I find these access methods in the plan? Well, I'm going to find them in the operations column of our plan. But how do I know what to do if I get the wrong access method? What if I see a full table scan when I expected an index, or vice versa? Well, the very first thing I do is I look at the cardinality estimate. And if that's accurate, then I'm going to look at the join order, because that may also influence the decision the optimizer is making for the access method. But before we do that, I want to take a minute and have you become the optimizer. We're going to play a little game these last few minutes of today's webinar. I want you to take a look at the query before you and become the optimizer. Now you know the rules. You've only got 9 choices of access methods. You've got a customers table that's got 10,000 rows in it, and you've got a primary key index on the customer ID column. The where clause predicate says customer ID is in 100, 200, or 100,000. Now it's a non-equality predicate on a primary key. What access method do you choose? Well, chances are you're going to use that primary key index. So it's either an index range scan or it's an index unique scan. And in this case, it turns out to be an index unique scan. Now you may be saying to yourself, hang on, Maria, you told me that if it's a non-equality predicate on a unique or primary key index, then it has to be an index range scan. And that is true unless the optimizer can transform that query or rewrite that query under the covers for you to turn that where clause predicate into an equality. And that's exactly what's happening here. Your in list was turned into a where clause predicate that said where the customer ID is equal to 100, or the customer ID is equal to 200, or the customer ID is equal to 100,000. That allowed us to go to and do an index unique scan 3 times, one for each of the values, and allowed us to get a much more accurate or efficient execution plan for that query. What about this one? Same customers table, same 10,000 rows, same primary key index. This time the customer ID is between 100 and 150. Index range scan, index unique scan. What do you think? Well, in this case, we can't do the same trick. Why? Because the optimizer doesn't know how many legitimate values you have between 100 and 150. And so it doesn't take the risk of rewriting the statement to have all 50 values. And so it simply does an index range scan. What about this case? Same customer table, same primary key, where the country name is equal to USA. Well, in this case, we don't actually have an index on the country table. Remember, your primary key index is on your customer ID. And so the access path chosen in this case is a full table scan because there is no index available to us. So what if I have some common problems? I'm using a table scan instead of an index, or I'm picking the wrong index. Well, if you're using a table scan instead of an index, that's often chosen because a parallel degree has been specified on the table, but not on the index. When you specify a parallel degree on the table, whatever degree you give it, you reduce the cost of the full table scan by that amount. So let's imagine the cost of a full table scan is 100. I put a parallel degree of 4 on that table, then the cost of the full table scan actually becomes 25 because we take the serial cost divided by the parallel degree to give us the parallel cost of doing that full table scan. And that can often make that full table scan far cheaper than the index. So something to be aware of. The other thing to be aware of, if somebody changes something called the multi-block read count, it's an init.error parameter that you shouldn't mess with, but if you do, it can seriously impact the cost of a full table scan. And what you may have done to fix one query could indeed break a large number of other queries. So please don't change that parameter. One of the other options you've got is you're picking the wrong index. This often happens if we've got stale statistics, or the cost of a full index access is actually cheaper than having to get the row ID from an index range scan and look up all of the rest of the column values from the table. So you've got to bear in mind that we are going to pick an index that has the most number of columns matching in that index over doing an index range scan followed by a table lookup by row ID to get those extra columns. So things to bear in mind. Now, we moved a little slower. I moved a little slower than I thought, but our time is up today. So what I'm going to do is quickly we'll cover all of the missing parts that we didn't cover right now next week. But our time is up right now. All the questions, and I thank everybody who's added some questions there for me. I'm going to get those questions after we finish up today, and I'll make sure I have the answers to all of those questions for you at the beginning of next week's seminar, because next week, August 18th, same time, same place, we are going to do part 2 of Explain the Explain plan, where we'll look at joins, join orders, parallel execution, and partitioning. All those aspects of the execution plan will be explained, and we'll be able to get into a lot more detail. And again, at the end of next week's session, I'll try and open it for Q&A so we can spend a little longer together and I can address those questions. But don't fear the questions that have gone into the chat today. I will get a copy of those and I will have the answers for those questions at the beginning of next week's session. But with that, I want to thank you so much for spending your time with me this morning. I hope what you heard today was useful, and you'll be excited to join me next week for part 2.
Thank you so much, Maria. We really appreciate your time and expertise today. Everyone, thank you so much for attending. NYOUG, thank you so much for your partnership. And just to address a few housekeeping questions here, we will be getting slides to you, don't worry. Someone from my team will be following up, and they'll have slides for you, a link to the recording for today's webinar, and also a link for you to register for next week. So don't miss out on part 2. Also in the chat section, I added a few notes for you there. If you'd like to register for Maria's another webinar she's hosting called The Future is Data Driven, that is hosted by the Chicago Oracle User Group and Midwest Oracle User Group. It's also complimentary conference, so definitely don't miss out. And with that, I guess we've got everything. So thank you all again. I'll give you maybe another minute to add additional questions. And yeah, I hope everyone has a great day. Until next time, take care.